Hi everyone, and welcome to our final thesis presentation. I'm Nouran Flaifel, along with my team members Ahmed Abdelrahman, Marwan Abbas, Mohamed Elatroush, and Zeyad Zaki. Our project is supervised by Dr. Mohamed Shalan and Dr. Tamer ElBatt. So for today's agenda, we're going to start by introducing our system, and then we're going to cover some system features. We're going to talk about our development tools, how to use our system deployment plan, and finally, our conclusion and future work. So let me first start by some statistics. So between 2015 and 2050, the global elderly population will nearly double from 12% to 22%. And until January 2019, Egypt's elderly population had reached 6.5 million, which is about 6.5%, and it's expected to increase up to 11% by 2026. And since the elderly population is massively increasing worldwide, monitoring their health and well-being is always a concern to their doctors and close relatives. And with our fast-paced lives, we can't dedicate enough time to spend with them, and they're left alone for long periods. Also, most of them will prefer their freedom and independence over being kept at senior care centers or having caregivers living with them full-time. Therefore, we want to be able to remotely monitor their well-being at the time when we aren't physically available. This problem has also been highlighted and became a bigger issue during the difficult times of COVID, since they're the ones with the highest risk, and we're trying to decrease or even avoid physical contact and regular visits. And now, let me leave you with a short movie to introduce our proposed solution about this problem.
Hi, meet Susan, her son Ahmed and his family, and her doctor. Susan lives alone. Ahmed is busy and doesn't always have the time to call or visit his mother regularly. Recently, due to COVID, Susan is keeping herself safe by staying in quarantine. There are a lot of people like Susan and her family. That's why we're introducing to you eCare System. The system consists of a mobile application, a smartwatch, and small devices that should be put in each room in the house. eCare offers a set of features: an indoor localization feature to know the location inside the house at any time, a communication channel between Susan and her caregivers, a fall detection feature to notify the caregivers in case Susan fell. We also have a health data tracking feature to check on Susan's health status. Thanks to eCare, Susan and her caregivers are now always connected.
And as we just saw in the video, our system hardware consists of a smartphone, a Fitbit smartwatch, and ESP32 for the indoor positioning system that should be put in each room. And for our system architecture, the smartwatch will be connected to the smartphone using Bluetooth Low Energy, and the smartphone will send the data over to the cloud using Wi-Fi. And for the ESP32, it will recognize the smartwatch using Bluetooth Low Energy, and it will also send the data over to the cloud using Wi-Fi. And now I will leave you with Mohamed Elatroush to talk to you more about the indoor positioning feature.
Okay, so one of the major features of eCare is the indoor positioning system. The IPS will be used to locate the patient within his house at all times, which is a very important piece of information to this patient's caregivers. For example, if a patient or a user stays inside a room for so long and he's not or she's not replying back to his or her caregiver, this piece of information would be useful. Also, the IPS will be used to detect any irregularities in the elderly daily routine. Considering the privacy issue, we've decided to use microcontrollers in different rooms instead of using webcams to monitor the elderly, because most of the elderly people do not prefer to be monitored through camera. Also, another advantage of our system, it's easy to deploy with just plugging in the ESP32s in the rooms that we think is the most important. So moving on to the implementation of the IPS, we used the ESP32 microcontrollers in most rooms in order to search and detect the Fitbit Sense MAC address. And if the ESP32 do detect the presence of the smartwatch within an RSSI received signal strength range, then a flag called value will be sent to the back end of our system, indicating that there's actually someone inside that room. alongside with an entry and an exit point with a timestamp. Now, the elderly location will be known 24/7 by their caregivers as it updates his current location on eCare's mobile application. So the received signal strength will be sent to the database, and a comparison will occur if there were two ESP32s detecting the presence of the smartwatch at the same time. So based on the least received signal strength, we've decided to select where the user is currently at. Also, we've used Arduino IDE in order to program the ESP32 to update the real-time database alongside with timestamps of entries and exits of each room. And now I'll show you a demo uh, about how our UI would look and how the real-time database updates in the IPS. So one of our members, his current location is unknown because he's not currently inside any room. And the bathroom and kitchen values are 0 because he's not in any room. So when he enters the kitchen, he's currently in the bathroom, so an entry 1 is generated with a timestamp. The number of entries got incremented, and the value of his presence is 1. So when he leaves the kitchen, the location should be unknown, as well as an exit point entry here. So right now his unknown location and an exit point with a timestamp is generated, and the value of his presence is not is 0, which means he's not in the kitchen. He's now inside the bathroom, so the bathroom ESP32 detects that he's entered there, and then entry 1 is generated with a number of entries incremented there, and the value is currently 1, and location is bathroom. Also, when he exits the bathroom, an exit point will be generated. The value will be 0. And now, Zeyad will talk more about the fall detection feature.
So our second feature was the fault detection feature. To start off, we needed to create our own dataset, and that is to make sure that the model will have a better accuracy if the training dataset was coming directly from the Fitbit sense, not from any other dataset online. So to do so, we created a clock face using Fitbit Studio. The user chooses the type of activity he wishes to perform. He performs it, then he sends it to our database. Both accelerometer and gyroscope readings are being recorded during the time period with frequency of 100 Hz, and the files are sent to our database in the following fashion: the type of the fall and its timestamp. We simulated the ADLs and the falls according to the sysfall dataset, which is the most commonly used in research, but we tweaked a little bit. We added more activities of daily living we found important, such as praying and others. So these are the 19 different ADLs we simulated, and these are the 15 different types of falls. Here is a demo of how we used our application to collect our dataset. We simply start the application, we simulate the fall, and then all we need to do is to stop, save it, and send it to our database. Now that we have the dataset ready, the next step would be how to create the fall detection algorithm. As you can see here, these are two different types of activities from our dataset, one being jogging quickly and the other being falling forward caused by a trip. Just by the naked eye, we can tell that thresholding here would be very tricky, as how can we use a threshold to differentiate between a fall and other daily activities? And that has been proven true by our extensive research that deep neural network have shown to be the go-to solution in terms of accuracy and efficiency when it comes to creating fall detection algorithms. So our proposed classifier is based on a recurrent neural network model with underlying LSTM blocks, which are called long short-term memory blocks. As you can see in the architecture, we have two of these LSTM blocks, and we designed the architecture to be light to consume as minimal power as possible. Also, we use weighted cross entropy as the balancing loss function to compensate for the strongly imbalanced dataset. The model accuracies reached true positive results of 85% and false positive results of only 10%. Finally, we reach the final part in the fault detection, which is integrating it within the system. In this picture, you can see the eCare Clockface app. It collects the sensor data reading and sends it to our database once per minute. It also runs in the background at all times, and it displays the heart rate of the patient as well. Cloud computing is used here to predict the faults and update the application's UI. More on that will be discussed further in the presentation. The watch battery lifetime of the eCare app running at all times takes 13 to 14 hours. Without the eCare app running, it takes from 18 to 20 hours. We wish to push our lifetime to 16 to 18 hours, and we have some ideas to do so. We will discuss it at the end of the presentation. This is a demo of the fall detection. As you can see here, after the fall happens, a file is being sent to our database, and after that, the Google Cloud function will automatically take this file, delete it, and feed it to the machine learning model, and it detects a fall and sends a notification to the UI. And now Ahmed will continue with more of our application features.
Okay, for health data tracking, we use all the publicly available Fitbit web APIs, except for the heart rate web API needing more authorization, which we got through communication with the Fitbit. And through these APIs, we were able to collect data for the heart rate, step count, calories, and total time sleeping, where we could generate reports to elaborate on the patient's well-being. Moving on, we created a communication channel between the patient and all its caregivers, which has easy accessibility buttons for the elderly to communicate faster, and also a feature that they can add scans of prescriptions for ease of use and to expedite the speed of getting such documents. And an emergency feature for in case anything happens, just it can ring all of its caregivers with just one button. Okay, moving on to the development tools. These are all the development tools that we used, and we used a total of 5 programming languages to complete our project. And we will elaborate more on the development tools. And the first of them being Firebase, which we use as our backend for to expedite the speed of creating our app, which is easily maintainable and flexible in many ways. The first of the service is Cloud Firestore, which we used as our database for the system. It's just a real-time cloud-based NoSQL database, which has flexible data model and querying. Moving on to the authentication, we use the preset models from Firebase, which have multiple sign-up methods and handle everything else. And moving on, we also use real-time database, which is the predecessor of Firestore, but due to the ease of its SDKs with Arduino, which we needed for the IPS system, we also incorporated it into our system. Also, our backend tools, which we deployed on Google Cloud Platform using the service which is Google Cloud Functions. First of all, since we were using Firebase, we didn't really need to deploy an entire backend on a server with giving that Firebase holds up a lot of that. Therefore, the backend code we needed to run, we chose to run on Google Cloud Functions, which is a pay-as-you-go function as a service, run code with zero service manager. These functions that we are running are the IPS data collection, the health data collection, and fall data detection prediction. And in order for these functions to run at the times we need, we use Cloud Scheduler, which creates cron jobs for each one to run at its allotted time. These are our system quality attributes: availability, that the system will be running 24/7, maintainability, that we aim to have it always be updating and fixing bugs. Also, usability, since most of our user base will be elderly, we wanted to make our user experience as easy as possible. And portability, we have made our app available for Android and iOS. Also, interoperability is all the system hardware and software components are interoperable and able to communicate with each other and exchange information. Okay, this is how to use setup. The caregiver only needs to set up an account and add the patient. However, for the patient, they need to be wearing a watch, and someone has to install the localization devices within their home. And also they need to create an account, and they accept the request of the caregiver, and then the system will be ready to go in operation. Okay, and now a couple of short videos for our app demo.
Okay, so now I'm going to demo the iOS application. We're going to sign up as a caregiver. We're going to write the name, the email, password, phone number. The relation is going to be caregiver. In other cases, it could be a doctor. We're going to sign up and we're going to enter the credentials we just created the account with. We're going to sign in. We're going to search for our patient. In this case, it's Nouran. We're going to send her a request and wait for her acceptance.
So this is the application from the Android side. I'm going to be logging in as a patient. And then I can go into my friend requests and accept the friend request that Nouran just sent me. And then I can go into the caregiver's profile and use these buttons to easily post something or send something like hi Marwan, or upload a document or send them an emergency. Then on my profile, I can see the post that I just sent to Marwan, or something like hey caregivers. And these posts can actually be seen by all my caregivers that I accepted their friend request, and I can also upload a document or view my status, and then I can edit my profile or change my profile picture and submit to the database.
Accepted our request. We can now view her profile and see her wall, and we can view her status. This is the her hourly heart rate. We can check her location. The location is currently unknown, but it should show her real-time current location. We can view the location history of each room, where it shows the date, the number of entries, and the duration spent in each room, and the same goes for the bathroom. And then we can view some health reports, her average heart rate per day, and the number of steps, and the number of calories, and the number of hours slept. We can also leave her a message, for example, hi, and this shows on her wall, and that's it for our application.
Okay, and now Marwan will continue.
For our system deployment plan, we are planning on maintaining our vision of keeping the system a community-based system. Therefore, it is a non-profit platform. Our package will consist of a Fitbit smartwatch and 4 ESP32s. We shared our vision and system goals with Fitbit and got a positive feedback from the sales operation manager, and got the opportunity to establish a custom storefront so that the customers can redeem and drop ship their smartwatch to their desired location. Also, we got a special discount on the first bulk of smartwatches only for eCare clients. As we are a non-profit platform, we have to cover our costs. So we calculated the costs before and after the discount we got. The Fitbit will be 70% of the retail value, which is $330 that comes down to $231. And because we will buy a big quantity of ESP32s from China, the ESP32 will cost $3.5 instead of $10. So the total initial cost is going to be $245. But as we also have our running costs, as the system is deployed on Google's Cloud Function for machine learning algorithms and data fetching, we estimated the running cost to be $30 per month. As you just saw, the price of the system is relatively high to the average customer. That's why we have a 5-year plan to subsidize the cost for the user, to help more people and increase our user reach. For the first 2 years, including this year, we are planning that the user would pay for the whole initial cost and running cost in the form of a monthly subscription. And by the year 2023, we are planning to subsidize the running cost so that the user can only pay for the initial cost. And finally, by the year 2025, we are planning on subsidizing part of the initial cost, and our goal is to subsidize 50% of the initial cost. But how are we going to subsidize the cost of the system? We have a few ideas. The first one is collecting donations, as we are a non-profit platform. or sponsorships from pharmaceutical companies and hospitals with added benefit to the company. And the final idea is keeping the monthly subscription to users who are interested in the premium user package, which has more features like booking hospital rooms, reordering medication automatically by a click of a button, or outdoors localization for their loved ones to know where they are outside their homes. And to conclude our final Thesis 2 presentation, we developed a working system consisting of a cross-platform mobile app, a clock face for Fitbit, 4 different features, and a machine learning algorithm for fall detection with a data set that will be published on Kaggle. For our next steps and future developments, we are planning on developing a smart algorithm to detect irregularities in daily routine other than thresholding. Processing the fall detection data on the smartwatch to detect irregularities before sending it to the cloud functions to analyze it and find if it's a fall. This would consume less power from the smartwatch as it would decrease the number of data sent to the server and be more economically efficient as the cloud functions won't need to be working 24/7. We are also planning to enhance our fall detection accuracy by enlarging the data set and asking the user, "Are you okay?" via the smartwatch before sending the notification. To help us enhance the model by reinforcing reinforcement learning and decreasing the false positive results. Finally, thank you all, and a special thanks to Dr. Mohamed Shalan and Dr. Tamer ElBatt for their constant support and help throughout this year.